Hello everyone, in this video we'll see the characteristic table and excitation of T flip-flop or the toggle flip-flop. So if we want only toggling action, we'll be using the T flip-flop or the toggle flip-flop. So the truth table corresponding to T flip-flop is like this. That is, if no clock pulse is given, then whatever be the value of T, output Qn plus 1 will be equal to Qn. So that is, it will act as memory or it will hold the state. Next is when a clock pulse is applied and if T is equal to 0, then Qn plus 1 will be equal to Qn. That is, it will again act as memory. That is, the next state will be equal to the present state. So it will act as memory or it will hold. And next is when the toggle input is 1, that means Qn plus 1 will be equal to Qn bar. Toggle input is 1 means J is equal to 1, K is equal to 1. So toggle flip-flop is obtained by combining the J and K inputs together. So when T is equal to 1, that means J is equal to 1, K is equal to 1. So corresponding to this case, Qn plus 1 will be equal to Qn bar. So this is the toggling case. So this is the truth table of toggle flip-flop. Now we'll write the characteristic table of T flip-flop. So characteristic table. The characteristic table will write Qn plus 1 in terms of Qn and T. Qn is the present state and T is the input. We will write the next state Qn plus 1 in terms of present state and the input, that is T. So there will be 4 cases 0, 0, 0, 1, 1, 0 and 1, 1. So the output Qn plus 1 will be, so corresponding to toggle input 0, what Qn plus 1 will be equal to Qn. So this is that condition. So when T is 0, Qn plus 1 will be equal to Qn. So that is, here Qn is 0, so Qn plus 1 will also be equal to 0. Now next case is when T is 1, then T is 1, Qn plus 1 will be equal to Qn bar. So here Qn is 0, so Qn bar will be equal to 1. So Qn plus 1 will be equal to 1. Next case is when T is 0, then Qn plus 1 will be equal to Qn. Here Qn is 1, so Qn plus 1 will be equal to 1. And the next case is when T is 1, then Qn plus 1 will be equal to Qn bar. So here Qn is 1, so Qn bar will be equal to 0. So this is the characteristic table of T flip-flop. Now we have to write the characteristic equation, that is Qn plus 1. So for that, we can write the characteristic equation directly by looking into this characteristic table. That is, we can see that for these two cases, the output is high. That means for odd number of inputs high, the output is high. So this means this can be written as Qn XOR T. So Qn XOR T is Qn T bar or Qn bar T. So that is Qn XOR T. So that is the characteristic equation. So we have written it directly from the characteristic table. As we can see, it is 1 for these two cases, and as for odd number of inputs, the output is high, so it corresponds to an XOR gate. So we have written Qn plus 1 as Qn XOR T. Now we can write the excitation table of T flip-flop. Excitation table is, we will be writing T based on the values of Qn and Qn plus 1. We will write what is T. So the transitions are 0, 0, 0, 1, 1, 0 and 1, 1. So correspondingly we will find what is T. So that we will write from the characteristic table. So we can see that corresponding to Qn 0, Qn plus 1 0, T is equal to 0. And when Qn is 0 and Qn plus 1 is 1, T is 1. When Qn is 1, Qn plus 1 is, that is the last case. When Qn is 1 and Qn plus 1 is 0, then it is equal to 1. T is equal to 1. And when it is 1 and 1, Qn is 1 and Qn plus 1 is 1, T is equal to 0. So that we can write over here. So this is the excitation table of a T flip-flop.